Let's talk about electronically controlled circuits. So in this way, we're still talking about switches, but no longer are we talking about straight up toggle switches, or at least not toggle switches directly controlling our outputs. We're talking about the fact that our inputs have to go through a controller to be sent to our outputs. And so that's sort of the way I've laid out the screen for us. On this side here, we have examples of some inputs. In the center, we have examples of controllers. And on this side here, we have examples of output devices. Now, those of you that are familiar with these devices, you'll know there's controllers built into these as well. And so they're more complex than I might be letting on. But the idea here is that we have to be familiar with the main components of our electronically controlled devices. And that means that we have to have an operator input, we have to have something that processes that operator input, and then we have to have a device that seems to do the work. And so what I have here is an example of an Arduino. This is an Elegoo Arduino board. And this here is actually the processor chip that can be programmed. This is internal inside the controller. Right here we have plugs, and these are going to be our terminals for our digital controls, so then we can have pins in and pins out from the digital side. We can have our powers and grounds right here, and we can have our analog inputs right here. We have our power supply coming in on these terminals. So this board provides the connections for the inputs and the outputs, so inputs and outputs. Okay, so it provides all of our terminals for all the things that have to wire in and wire out, and provides the structure to allow all of those terminals to connect with the actual processor itself. This device right here is the thing that does all of the processing, taking the inputs, comparing it against a program or a parameter, and sending an output out. So these terminals, usually you can poke them in, and they're meant to be worked with this breadboard, so we can even pull pieces off and we'd just be able to stab in there, right? So they're handy enough, but that doesn't work great in vehicles because we have a lot of vibration and things that are moving. So instead, we end up with these connectors right here. So they are locked connectors that have indexes. So they usually have a key system on there to make sure that the wiring goes in the right position. And connected to here are going to be all of our harnesses and all of our wiring. That harness and wiring is going to include the same as it does on this little board, some powers. So we're going to provide power and ground in some of these terminals. We're going to have some input wires. This one says analog input, so we're going to have some input wires. We're going to have some power and ground wires. We're going to have some output wires that are supposed to do their job. And that's exactly what's going on in this controller. Some of these pins are going to be positive. Some of these pins are supposed to go to chassis ground. Some of these are supposed to be connected to sensors, and some of these are supposed to be connected to load devices. You need a schematic for you to understand what the pinout is. That is what you need. You require that from the manufacturer to know what all the pins actually mean. When we look at these units right here, we can see there's lots of pins. And so some window controllers actually are a controller. They have a process card in there. They take the switch inputs from the buttons the operator would push, and they only send a network or communication under 2 wires, sometimes 4, to the processor for the processor to know what the operator wanted. This one actually has enough pin locations that the switches are represented at the pins and are communicated into our controllers. Now, these are not related systems. I'm just showing you examples of inputs, controllers, and outputs. At no point does our traction control actuator, our 4-wheel drive actuator, get controlled by our windows, our window controller. If it did, we definitely have a wiring problem. Okay, so don't misunderstand what we're saying. We're only talking about inputs, controllers, and outputs. So there are different kinds of inputs. Sometimes our inputs are complex units like this, that you would have to open them up to see exactly what that switch does. Using a schematic, we will be able to see where is the power and where is it supposed to go. Is it positive switching or is it ground switching for this window actuation. And then what pins are we supposed to work with? On simpler switches, like this double pull, double throw switch, these ones all follow a very universal input on the center and either continuity to one side or continuity to the other. So once you're familiar with troubleshooting a double pull, double throw switch, you can just go to work testing it. Other times, our controllers need more complex inputs, and these more complex inputs can come from all sorts of different switches. Sometimes they can come from things called potentiometers. And so these potentiometers are super small. You'll find them on your dash. We put bigger knobs on them because nobody wants to operate such a small thing. And they are actually a voltage range. They get sent a reference voltage and they send a signal voltage to the controller. And so the switching portion of the controller happens because we've given it a program that says when this is in the range of 2 volts to 4 volts, we want you to do something. If we're not within that 2 volts or to 4 volts, don't do anything. And so now it's programming that's taking over, and it's taking the operator input and translating it into action. But it's not as simple as simply flicking a switch anymore. In the same way, sometimes we have a photo sensor. That's what this one is. So this is a photo switch that as light shines on it, the resistance value changes, which is going to change the voltage or potential that goes across the switch. Now you can write a parameter for the program to be able to respond to the light that hits the switch. And so while it's not as simple as saying infinite resistance or zero resistance like a toggle switch would have, instead, maybe it's a parameter that says, well, when it's at 1,000 ohms of resistance, it's off. And when it's at 100 ohms, it's on. But a lot of the time in these electronic controls, it's even greater than that. Sometimes they're in the thousands of ohms to hundreds of thousands of ohms in the difference between on and off. And that's because in an electronically controlled device, we don't need a lot of current to tell the operator intent. Instead, we just need the presence of voltage. And so this allows our devices to be made significantly smaller while still performing the work. But once the operator's intended operation has been sent to the controller compares it against the parameter. It's been told the range. When this, I do this. When that, I do that. And it sends its output signals down to our actuators. Now, our actuators are just simply the things that do the work. So this is a motor attached to our traction control, or our transfer case, for our actuation of our four-wheel drive. So that's our transfer case actuator. Another version of an output could be simply a buzzer. If you have a vehicle that when you have an alarm or when the keys are left in the ignition, it goes ding, 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 ding. Well, that's an output to a speaker from a controller. Maybe you have a motor that seems to move. Maybe you are operating your mirror controls. You're saying left mirror, and I'm controlling it. And your controller is now going to send a varying voltage to a servo, and a servo is responsible to move a particular amount of movement, and it has limits. It's not just a simple motor, it's a motor with a feedback link that says I moved to where you wanted me to be and I stayed there. And so it gets a reference voltage, it gets to where it's supposed to do and stays there. Sometimes our output devices are as simple as a light or an LED. And so then our controller becomes, and this is the troubling part when we troubleshoot electronically controlled system, we struggle with who is who in the zoo. When our switch is telling our controller what to do, this is the switch, our battery is the source, and the controller is the load. But when the controller is telling something to happen, so the servo to operate, the alarm to turn on, the LED to turn on, the motor to operate, it becomes the source in the circuit. It needs a source, but it becomes the source, and it sends that voltage to a load, and from the load it has to either go back, sometimes it goes back into our controller to go to ground, and sometimes it has its own ground and it goes to chassis ground. And so sometimes, just like in a relay we have two circuits. We have a control circuit, the 85 and 86, and the load circuit, the 30 to 87. The same way, our electronically controlled systems have two circuits. We have our input circuit, and separately, we have our output circuit. And it's the programming that happens within the controller, the actual chips themselves, that make the connection from the input to the output circuit. And so this is where it starts to get a little more challenging. But what I found helpful as I've worked in this industry is keep them separate. Remember that the ECM needs its inputs. So if it's supposed to get positive power into that pin, make sure that pin is getting the power it's supposed to get. So you can do that through resistance checks back through the switch, back through the wiring, or you can do it through a voltage drop check with back probing or breakout boxes using good practices. And in the same way, if your device is supposed to be working and the source, it's being sent its power from a controller, then you need to treat the controller like the source, and you need to say, okay, if pin 11 is sending the power for this motor, is power available at the motor? And if it's not, is it being sent from pin 11? If it's present at pin 11 but not at the motor, then the wire between the controller and the motor is the problem. And this is where good troubleshooting techniques of identifying the 4-step rules really come into play, which we'll cover in a different module.